The point where the expansion tank is connected to the system is known as the point of no pressure change. We've been taught for many years to pump away from this point, but why? With this model, we can explore that question and hope to provide you with a better understanding of the point of no pressure change and why we always pump away from it. We start with the expansion tank isolated from the system with ball valves. The pressure on the system is set to a typical 12 psi. Make note that the static pressure at the bottom of the system is not the same as the pressure at the top. In this example, 20 feet represents over 8 psi of pressure drop to get the water to the top of the system. This leaves less than 4 psi at the top of the system even with the circulator off. When we power the circulator, it provides a delta P or difference in pressure. How much difference depends on the circulator, but it's important to remember that a circulator will always create a differential pressure when energized. In this example, our circulator generates a differential or delta P of 6 psi. This increases the static pressure of 12 psi at the discharge of the circulator to a dynamic pressure of 18 psi. If we subtract the pressure required to get to the top of the system, 18 psi discharge minus 8 psi pressure drop, we are left with less than 10 psi at the top of our system. But how does the circulator work if the expansion tank is isolated? The answer is very simple. The circulator has no effect on how the expansion tank functions. We use an expansion tank because fluid expands as it is heated. The expansion tank allows a place for this expanded water to go. But since the circulator cannot increase or decrease water volume, it cannot affect the pressure at the expansion tank. This is why where we connect the expansion tank to the system is referred to as the point of no pressure change. Let's look at what happens when the expansion tank is open to the suction side of the circulator. In this correct scenario, we are pumping away from the expansion tank or the point of no pressure change. And as you can see, nothing really changes. The circulator is able to increase the discharge pressure and flow water to the top of the system using that pressure. But if we open the other valve and move the point of no pressure change to the outlet of the circulator, we can see the immediate result of pumping into the point of no pressure change. Previously, with the expansion tank in the correct position, we were able to achieve 18 psi on the discharge of the circulator. But now that we're pumping into the point of no pressure change, we can only achieve the pressure at that point. Since the expansion tank is charged to match the system pressure, in this case 12 psi, the circulator is unable to increase the pressure beyond 12 psi at that point. So our discharge pressure at the circulator is 12 psi. But remember, the circulator will create a pressure differential. If it cannot boost the outlet or discharge pressure, it will reduce the suction pressure. Now, instead of having 12 psi on the suction of the circulator, we have 6. So discharge pressure at 12 psi minus 8 psi drop to get to the top of the system equals less than 4 psi at the top of the system. 4 psi at the top minus the 6 psi suction pressure on the circulator means we could have a minus 2 psig at the top of the system in this scenario. Circulators require static pressure to operate and will not flow water at zero pressure. So this is a real problem, and not only means we will have no flow at the top of the system, but we could even pull air into the system through our air vents. This is why we pump away from the expansion tank or the point of no pressure change.